Everyone hear me? Mic is working, good? Okay, excellent. So thank you all for being here and good morning. Thanks for making it for the first talk of the day. It's really a pleasure to be here and to be talking about the inner disk and inner disk chemistry. I think this is a topic that's really coming into a really fruitful age for what we're going to learn about the inner disk and what's going on there. So I don't have to motivate for this audience why we care about the inner disk, but just to remind us, look, this is where we think that most planets are going to form, in these protoplanetary disks. And so because of that, we really want to know what ingredients are available for these planets as they're forming. As the planetesimals are coming together, as the planets are starting to accrete their atmospheres, we want to know what material is there to be incorporated into these forming planets. But I'll also argue that the inner disk chemistry and the inner disk composition can also tell us about the disk structure and the disk evolution in a way that is very unique. And so not only by studying the composition can we tell what is there, but we can also tell things about what is happening in the system more generally. And so the way that we're doing this, and the way that I'm doing this in this talk, is by using JWST observations, which are really attuned to the warm, dense gas in the inner regions of these protoplanetary disks. So we have our molecules there in our disks, and we're observing them with JWST, and this is the kind of, this is a mock spectrum of what we would expect to observe in JWST's MIRI instrument in the MRS mode. So we have CO at the shortest wavelengths, we have C2H2 and HCN, and CO2 and OH, and then we have this plethora of water lines across the MIRI MRS spectrum, which can tell us a lot about the properties of water in the inner disks. These are the kind of most plentiful molecules that we expect to see. With Spitzer, these are the molecules that were most commonly observed in disks around sun-like stars. And so this is kind of what we would expect to see in our data. And so if you sum all of that up, it looks something like this, where we have all of these molecular lines making this kind of forest of emission, where we then have to tease out what molecules are there and what the properties are. And so what do the real data look like? This is just slab models added together. But what do the real data show us? And before I show that, I just want to say that it's been a really busy few years. This is an incomplete list. This is my non-exhaustive list of papers that have been published on disk chemistry from JWST. So you can take a picture now, but when the slides are posted, feel free to go back and use this as kind of a non-exhaustive reference for where you can find some really interesting papers on a variety of topics. And so I can't obviously cover all of this here in this talk, but this is a reference point for kind of where we're at and what we've learned so far. So with that being said, here are a sample of objects observed with JWST MIRI MRS. This is data from the MINES GTO program, which is a program led by Thomas Henning at MPIA. And so I've selected just a sample of targets here, where this is the flux versus wavelength for each of these targets from 5 to 25 micron or so. And what we can see in these targets is that there is a huge diversity in the spectra that we see. There is a diversity in the line strengths. So we have objects that are very line rich and these very strong molecular lines. This, for instance, is mostly all water here. And then there are objects that are line poor, where they're very weak in their molecular emission. The molecular species are different between all of these different targets. Again, this is filled with water lines, this one as well, but this one is full of hydrocarbons with very little or no water present at all. And so we're seeing differences in the inner disk composition as well. And then I won't focus on this today in this talk, but also we see a variety of the different dust features, probing different grain sizes and grain compositions in the inner disks of these systems. And so it may not be such a surprise, right, that we see this kind of diversity in all of these different targets, because these are all different systems. They have different evolutionary processes, they're around different types of stars, their disk structures are different. And so maybe it's not such a surprise then that we see such a zoo of molecular spectra from these targets. We have large disks with many rings. This is TW Hydra, for instance, here. We have targets with planets. This is PDS-70, so I'll talk about PDS-70 later. We have this close, very close binary system, DF Tau, where we have 2 disks in the system, but both are very, very small. They're less than 3 AU in size. So essentially all of this emission is coming from the entirety of the disk. There is no outer disk in this system to really be providing any additional material. And so with this kind of diversity in all of these spectra, the goal is to do kind of deep dives into individual systems. Doing that, we can use complementary observations, detailed modeling works to really try to get at the processes that are happening in individual systems. But then, of course, we also want to use statistics. We want to use large samples to look for trends with the system properties. And so there's a range of system properties that we can probe: the disk structure, the stellar mass, the age of the system, things like that. And so then we can start to really learn kind of more generally what is happening in these systems. And so we want to use both of these together to try to understand these systems in more detail. So I want to start with the delivery of water to the terrestrial planet-forming zone. So Jehan talked about this yesterday, and I'll just touch on kind of where we're at on that and what the picture kind of looks like now. So we have our protoplanetary disk, and we have our ice-covered grains in the outer disk. With time, these dust grains will drift inwards via radial drift. These dust grains will cross the water snow line, and that water ice will be evaporated, sublimated into the gas phase, where we can then observe it with JWST. So then the story goes is that if we have lots of this radial drift happening, and this is an efficient process, that we're going to enrich this inner disk in lots of water. If we stop that radial drift, for instance, if we have a planet here that is locking up these icy grains in the outer disk, then we might deprive the inner disk of some of this water emission. And so we might have a relatively dry inner disk. And so that's this hypothesis that Andrea Bonzatti put forward in 2020 using the Spitzer data, was that maybe these small disks will be enriched in water. And that's what they found. This was Andrea's 2023 paper as part of the JDisks collaboration, which showed in this system of 4 disks that extended disks that had not undergone efficient radial drift, were lacking in some of the water emission that was present in the disks that were very compact. And so this is the same plot what Jehan showed yesterday, which is that the compact disks showed in particular an excess of cold water. And so this was coming from these icy grains that had crossed the water snow line. So this story is amazing, and is telling us about the transport of material from the outer disk to the inner disk, and about the transport of water through these systems. But the situation is a bit more complicated. Not all disks are going to behave in exactly the way that we think that they should, right? And reality is complicated. So for instance, even if you have this radial drift coming in, and that's very efficient, if you have an inner cavity in this disk, that will carve out some of this water emission. And so you might be left with an inner disk that is actually relatively dry. So this is kind of the opposite of what we'd expect for these radially compact disks. On the other hand, just because you have a trap in the outer disk does not necessarily mean that that trap is efficient or completely efficient at stopping the radial drift of material inwards. And so if you have a leaky trap here, you can still have these pebbles coated in these ice grains, or even small dust grains coated in ice, making their way through the cavity, through the gap, and enriching your inner disk in water. And so the situation is just slightly more complicated than what we would expect. So I'll talk about this first example here of this inner cavity. So this is one of the first disks that we looked at with JWST. This is GW Loop. This is from a paper of mine 2 years ago, where you can see the mid-infrared spectra in black here in the spectral region from 13 to 17 micron in GW Loop. The data are in black compared to this total model in red. And so we can see evidence of C2H2 and HCN and OH and really bright CO2 and 13CO2 in the system. And there is water emission present in this disk, but it's relatively weak, and it's quite a bit weaker than in a lot of the other systems that we see. And so the idea here, one of the ideas that we put forward in this paper was that this is a potential evidence for an inner cavity in the system. So if you have this typical full disk system, you will have this full reservoir of water vapor in the inner disk. But if you have a cavity in the inner disk, you're carving out that water emission, making the disk relatively devoid of water in the inner region. And this has now been used to explain a couple of other sources, MY loop and CX tau, and there's modeling work with 2D thermochemical models which show that this can produce the observations that we see. So if I go back to this cartoon here of this system where we have this deep cavity that is blocking this material in the outer disk, this system is really only reminiscent of one system in particular, which is PDS-70, which we talked about yesterday. I'm sure it needs no introduction, but we have a small inner disk here, 2 giant planets in this cavity, and then this outer dust ring. And what we found with JWST is that in this inner disk, there is water present in this system. So I think that this is incredible. I mean, we see water emission coming from a system where we know planets to be forming. And if there are further planets forming in the inner disk, we know that they have water available to them as they're forming. But what this is also telling us is that there are indications in this system that water is coming from the outer disk to the inner disk. In this system that has 2 giant planets, and from the millimeter dust continuum, has a huge cavity. So we can't even stop drift from happening in this system where, by all means, I mean, it should be the most efficient at stopping radial drift from happening. So even in this system, it doesn't seem like the traps are totally able to stop all of the material from coming inwards. So I think in order to really link the inner and outer disks, we need complementary observations. So we have kind of the inner disk gas chemistry, but we really need to understand the disks more generally and the structure from both the very, very inner disk also to the outer disk. And we also need detailed modeling work to try to connect these things. And so I think from the inner disk side, we need high spectral resolution observations of the inner disk gas. So that's observations like VLT CryoRes Plus and Keck Spec and IRTF iShell. That can tell us about the gas kinematics in the inner disk to tell us if there are these cavities present in these systems. Similarly, we can use the optical and the near-infrared interferometry to tell us about the structure of the inner disk at scales that are unprobable by ALMA to tell us if there are these cavities in these inner systems. And then in the outer disk, there's a really nice suite of programs that are starting to connect the inner and outer disk chemistries. So DECO, this large program from ALMA led by Ilse Cleves, this has this beautiful gas chemistry observations in the outer disk, and they now have this inner disk component with JWST to try to connect the two. Similarly with AgePro, Paola is here, one of the co-PIs of AgePro, looking at the disk evolution, now also has a JWST component. And so we can start to link there the evolution of the outer disk with the inner disk chemistry. And programs like DSharp as well, where we have all this beautiful ALMA data, there are complementary JWST data in a program led by Colette Salick. And so I'll just point out this paper from last year where we had to use all of these instruments to understand a very unique system. And this system is DF tau. It's this close binary system. But I think this paper was an example of the power of combining ground-based high spectral resolution observations, VLT, gravity observations, JWST, and ALMA. And if you put all of that suite together, I think then you can really start to make really detailed understandings of what's happening in these systems. So that was kind of showing the complexity that we're seeing. The story is not always so simple as we would like to think it is. The disks are behaving as they behave, and the trends are not quite as strong as maybe we would like. And so we need all of this additional work in order to start to tease out what these trends are telling us. But now I want to go to the trend that we find what is really strong. We find a really strong trend, and I think it's really interesting, and I think it's what's driving a lot of the work being done in the next few years. And that's this dichotomy between the chemistry that we see in disks around sun-like stars compared to the disks around very low mass stars, where very low mass stars, I'm saying, are less than 0.2 solar masses here. So I've taken the same spectral region, and I've taken all of the MINES sources, and I've averaged the spectra to get the average disk spectra of a sun-like star and the average disk spectra of a very low mass star. And you can see, without knowing what all of these lines are, that they are very different from each other. These spectra do not look the same, and they're telling us something about the inner disk composition. And so the disks around the sun-like stars, I showed you that there's a variety in the water richness, but in general, they are water rich. There are lots of water lines in these disks around sun-like stars. So that's what I'm showing here. That's what all of these blue lines here are in the data. By comparison, the disks around the sun-like stars are very carbon-rich, and they're very oxygen-poor. So the brightest thing in any of these spectra is C2H2, which we see also in the T-Tauri, but much weaker. So we see C2H2 and its 13C isotopolog. We see HCN. We see benzene rings. C6H6. That's a huge hydrocarbon in these disks around these very low mass stars. And this is commonly detected. This is the average spectra here. And so this is frequently detected in these disks around these low mass stars. We have CO2. That's really our only reliable oxygen carrier in these disks. And then we have things like HC3N and these other longer hydrocarbon chains. And so it's a really different chemistry of what's happening in these systems. And so if I just take the flux of C2H2 here in red, compared to the flux of the water lines, or here I've selected these water lines at 17 micron, and you plot that flux ratio as a function of stellar luminosity, you see a really clear trend in the data. I mean, this is showing this kind of continuum from being oxygen-rich in the T-Tauri stars to being carbon-rich in the very low-mass stars. And there is a diversity. So we do see, quite a bit of scatter here, especially in the T-Tauri stars, where that's telling us something about the inner disk chemistry is more complicated there. But in general, we do see this strong correlation with the stellar luminosity. And so how can we understand what is happening in these systems? There are a lot of things that are different between low mass stars and higher mass stars. And it's not so easy to disentangle which one is driving the differences in the chemistry. So the disks around higher mass stars, they're hotter, their snow lines are farther out, they're undergoing slower dust processing in a lot of ways, and they're in general capable of forming these giant planets, which can lock up at least slightly material in the outer disk. The disks around the low mass stars, by comparison, are much colder. The snow lines are much farther in. The dust is evolving more rapidly in both the settling and the dust drift, which I'll talk about next. And in general, they're not going to be forming giant planets that are more capable of locking up material in the outer disk. And so if we focus on these disks around these low mass stars in the faster dust timescales for these systems, there's this idea put forward by Ma et al. In 2023, which used simulations to show that if you bring in all of that, if you have a very efficient radial drift in these systems, that brings in all of these oxygen-rich ices very early into the disk lifetime. So initially, the inner disks are very oxygen-rich. That gas is then accreted onto the star and lost to the system. And so then by the time we're observing them at 1 to 2 million years old, we might only have this carbon-rich gas left. And so that's a current kind of leading hypothesis for what is happening in these systems. And it can also explain the rare water-rich spectra that we see. There's this example, SZ114, which shows this extended dust disk and a water-rich spectrum. So if we're able to prolong that water enrichment through leaky traps, that might be able to explain the oxygen enrichment in that system. But Feng will talk about this in her talk as well to show that this kind of story seems to be holding true. But it can also be a lower optical depth effect. So these disks are undergoing rapid settling, and so we're maybe just able to probe deeper into these disks than we are in disks around sun-like stars. And I just want to highlight, I just want to emphasize really, that these are the most common stars in the galaxy. I mean, the IMF is peaking at these targets. And these are also the targets that have the most terrestrial exoplanets. So that was also reinforced by Jesse's talk yesterday. So these are the most common formation sites of terrestrial planets, and we know relatively little about their formation environments. And so we really need complementary observations. It's really important when we start to understand these systems more generally. They're really faint, and so they take a lot of time, observing time, to get good data. But I think that it's really imperative that we start to look at these systems in greater detail. And so we're starting to make some progress. There's high angular resolution observations from ALMA, and also taking the objects where we have high resolution observations and getting the JWST data. So Feng has 2 programs on that. And then we're also trying to get the outer disk gas chemistry to compare with the inner disk. So we're making progress, but it's a work in progress, definitely. So then I want to go down to even lower masses. I want to go down to the planetary mass regime. And so the way that we can do this is via directly imaged planets. And now I just want to put this caveat out there because it's a polarizing subject, it seems. I know that most of these targets do not form like planets. These are pretty massive objects, you know, they're borderline between planets and brown dwarfs, and they often exist at large separations, which is why we're able to do direct imaging of them. So they probably do not form like planets. Maybe in some cases they do, probably most of them don't. But I think that if many of the processes in these systems scale with mass, then these are giant planet analogs that we can use to study disk evolution around them. And so I think that this is really a direct window into circumplanetary disks. So I want to show CT-CHA-b. It's this Titori disk, Titori star with a disk, and then there's this companion CT-CHA-b. When we take the JWST observations, you just see bright CT-CHA-a. But if you subtract that starlight and that disk component from A, you can see the faint companion there. And if you take the spectrum of that companion, if you extract the spectrum at that location, you see what we see in many of the isolated systems, this carbon-rich chemistry in this CPD-like system. So I'm not going to claim this is a real CPD, but it's behaving much like our isolated systems. Also with some unidentified features that we have yet to characterize. And so far the trend holds to even lower masses in stellar luminosities and central source luminosities. And so I think this is really an opportunity to study disk evolution around the lowest mass sources. And so by the end of cycle 4, we will have a complete sample of the 9 planetary mass companions with disks that we can observe with JWST. And so I list those here, and the ones in bold are from programs being led by Gabriela Cugno and myself. And here I show 5 of those sources and their SEDs, showing that we're going to be probing a range of evolutionary states for these systems. And so I think by studying these circumplanetary disks at a range of properties, we can start to understand the processes that are happening in circumplanetary disks, seeing how these processes and this chemistry scales with mass. So this is kind of the summary slide here. The disks around Titori stars are very rich in water, but with a great diversity, and that's telling us a lot about the disk structure and evolution. The disks around low mass objects are instead very carbon rich, and we think that that is related to the outer disk evolution, but we really need the complementary observations in order to tell. And then for the first time, we're really starting to get these circumplanetary disks, caveats included, which are showing us this carbon-rich chemistry, but which we'll be able to tell much more in the next few years. And so I think with these large samples, and with the complementary data, and with modeling, I think that we're really in a golden age where we can really start to understand the inner disk chemistry and what is driving it, and what it means for planets and potentially moons and satellites that are forming in this region. So with that, thank you.
Thanks for starting us out with such a great talk. Let's go over to the mic over here.
Very nice. Jack Lissauer, NASA Ames. You said in PDS 70, the presence of water in the inner disk implies leakage. What is different about water being there than just there being a disk that implies leakage across the gap? If the disk drains, if the disk doesn't drain on a rapid enough time scale, why do you need leakage across the gap?
Yeah, so it's a great question. So you can also get water formation in situ, so just via the gas chemistry happening in the inner disk. So this isn't from Giulia Parati's work, that they discussed some water could be coming from the outer disk, but also in this work by Danny Gassman earlier this year showed that PDS 70 also has this cold water emission that has been suggested to come from the sublimation of ices from the outer disk. And so that could be a way of doing this. And then there's also the ALMA data, which show that the inner cavity there is not so gas poor. And so that's another hint that there is transport from the outer disk. Yeah.
Hello, could you go back to your slide where you showed the flux ratio trend with stellar luminosity?
Yeah.
Yeah, so this does kind of look like there's a jump there instead of like a smooth transition. So do you have any explanation as to why this might be a process where there's a jump instead of more of a smooth transition?
Yeah, I think that's a great question. So I think that we do need more targets kind of in this transition region. But from the gas chemistry, you can get this kind of jump when you cross C over O of 1. So that's when you get the composition in the inner disk to be have just enough carbon to be, or just a little oxygen to be C over O of 1, greater than 1, then you can start to see this hydrocarbon chemistry start to come into play. So that could be a reason for the jump as well.
Okay, thank you.
Lauren Weiss, University of Notre Dame, Sierra. Thank you for this amazing talk. I learned so much from it. Can you go back to the slide, the cartoon comparing the disks of the high and low mass stars, basically the cartoon version explaining this? Yeah, perfect. Okay, so actually I want to throw an idea out here. I'm giving a talk on Thursday. I'll reiterate this idea at that time. I don't think giant planets are doing a whole lot here. Here's why not. You do mention that the sun-like stars are capable of forming giant planets. Even so, the occurrence of Jupiters is of order like 15 or 20%. So most sun-like stars don't actually have Jupiter analogs. So that's thing number one. Thing number two is I just did a really big survey of relationships between inner transiting planets and Jovians. And one thing that I have found is that the inner companions to the Jovians don't look very different in terms of their sizes, masses, and orbital distances from a comparison sample without Jovians, which is to say, I don't think the giant planets are very effective at sequestering material from the outer disk. So yeah, I guess either it's just the inner disk chemistry itself that matters, or if the outer disk chemistry does end up mattering, the giant planets are not doing a good job of stopping the material.
Yeah, I think that's a great point, and I think that's something that we see in PDS 70 as well. Yeah, if we can't block transport even in that system, then it's not as effective maybe as we pretend sometimes. So yeah, I think it's a great point. I think it can have influences on the inner disk chemistry, but exactly how and it depends on when these planets form too, and where they form, how that's going to impact the inner disk chemistry. Yeah.
Thank you.
Thanks.
Joseph Forga from Concordia Observatory. I have two short questions. So one about the stars, about these very low mass stars. Do they show increased C over O ratio? I mean, the stellar atmosphere.
Yeah, that's a great question. So I think that we don't have a lot of good constraints on the C over O ratio of these very low mass stars. Where I think that we can really start to do this is in the planetary mass companions. Because so much of the work on these directly imaged planets has been on characterizing the planet atmospheres, there are good constraints on the C to O ratios in those systems that we can now compare to the disk chemistry. In CT Child B and in some of these other cases, it looks like the C to O ratio in the planets are normal. And so if we see that the C over O ratio in the disk is very high, maybe that's telling us that the C over O ratio in the planet is being set early and is not being as influenced by the disk chemistry.
Yeah. Okay, thanks.
Lee Hartman, University of Michigan. So could you walk me through a little bit some of the things about the loss of oxygen? So here's the question. So the pebbles come in, they drop their oxygen, they drop their water, right? And then unless that stuff accretes, it's just going to sit there. And so it's going to be oxygen rich, right?
Yeah.
So if the alpha is low enough, maybe it doesn't go anywhere.
Yeah.
And then if you have a disk wind, right, if that's where the accretion, that comes in the surface layers, right? So that's not necessarily getting rid of the, you're just kind of sloughing stuff off the top and maybe even bringing in stuff from outside, and that's what you see in the upper layers. So it seems a little complicated to me. Could you talk about that?
Yeah, I mean, it's a great question. I think that we don't have all of the details figured out. I think that the idea is that that gas is being accreted onto the star early. If it doesn't, then that would change the picture, right? As you said, all of that oxygen-rich gas would then stay there. And so we want to look for trends with age to see if we do see this age dependence on the C over O ratio. Yeah, it's a really good question. And I think that all of these things can act in concert with each other. So the outer disk evolution, this radial drift, that can be coming into play, but it's also the settling of the disks that's allowing us to probe deeper in. So I think that there's lots of things together. And so I think I'm not necessarily subscribing to one idea that this is the cause. I think we need more data to say for sure, and modeling.
Hi, Marcelo Barraza from MIT. So maybe I'm not updated in the literature, but I thought that the water snow line was sort of a location for planet formation, and maybe there is some substructure there. So what's preventing that from forming? What can you say about the physics around this location from your observations?
Yeah, it's a good question. The snow line in these systems is really, really close in. I can't remember exactly where it would be in these systems. I have some mock numbers that I can look up later, but it's really close in. And so I think at those kinds of radii, are you really able to lock things up very efficiently? I'm not so sure. And if they're not forming anything very large, then that's not going to form deep enough cavities, I think, anyway. Yeah.
What about the T Tauris?
Yeah, the T Tauris, I mean, I think, so in these examples where we think that the water emission is weak because we may have an inner cavity, I think that we have to show with the observations that that's actually true. I think that remains to be seen a little bit. It shows in the modeling work that if you do form this cavity in the inner regions, kind of between the water snow line and the CO2 snow line, that you can reproduce the observations. And now we need to see if that is actually taking place in these systems.
Thank you.
Thanks.
Paola Pinilla, UCL. So I had a question related to exoplanets, actually, and it was partially answered by one of the questions before. So if there is no evidence that the inner planets are different in shape when they have a Jovian planet outside, do we have any evidence, and this may be a question for the audience, about the atmospheres and if we do have something that says that the atmosphere of an inner planet is different, or a periloma star that have a giant planet versus a solar type star. I would love to see that. So I don't know if there is any example that that we can cite for this.
Yeah, I would also love to see that. So I think that's a good question. Yeah. The question is about do we see differences in the compositions, the atmospheres of inner planets in systems where there is an outer Jovian, a Jupiter mass planet or not? And I don't know the answer, but I think it's a great question.
Bennett Skinner, McMaster University. You mentioned that this trend appears like it might be continuing, that around in circumplanetary disks we have really carbon-enriched chemistry. How does this connect to the fact that whenever we look at the Jovian and Saturn's satellites, that these are like very water-rich satellites?
Yeah, that's a good question. And I think that's something that we're really just starting to explore. I mean, there's a great diversity in the moons in the solar system and what their properties are. And so I think that there's a lot of work to be done to connect those two. It's not something that we necessarily have the answers for yet. Yeah, so it's a great question and something that we're definitely thinking about.
Ralph Putters, McMaster. In the idea that pebbles are getting through these large cavity regions, is it possible to see them? You know what the flux should be from your water measurements, make that clear, what the delivery should be to the interior. So that depends on the Stokes number of the stuff that's getting through. It can't be too high or too low, I suppose. So do you have a constraint on the visibility of that cavity flow of pebbles that you need?
Yeah, that's a great question. So I don't have those numbers, but I think that's a really interesting question, and one that I think that we can start to tease out. So yeah, I don't have the answer. I think it's a really good idea. We'll need the complementary ALMA observations to see if that makes sense or not. And it depends on the grain sizes, right? If it's these tiny pebbles that still have enough ice on them, then we can explain it that way, and we may not necessarily see it. So it's something to be explored. Yeah.
Thank you.
Hello, Arturo Ceballos from UNLV. I have a question. If you have a comment about we talk about the ice line and how it influences the C2O ratio in the inner region. Do you have a comment about the silicate line? As pebbles drift in, they should start to also be destroyed. So does that, or is there any indication in the observations that this is happening?
Yeah, that's a good question. I think that's happening at radii closer in than we're probing with the JWST observations. But it is something that we're thinking about also for these carbon-rich observations, these carbon-rich disks, if potentially some carbon grains are being destroyed. So this is Ted's carbon soot line idea, is if we're destroying these carbon grains, then that can release carbon into the gas phase as well. And maybe we don't need to destroy them, maybe we just need to erode them a little bit. And so I think that there's a lot of dust physics also here at play, and it's going to take more detailed modeling, I think, to say more. Thanks.